Hey guys, how you doing? It's Coach Scott, and this is our Unit 7 review on the periodic table. And I want to talk real quick about um, the FR top questions you may see, right? And I really want you guys to understand how these periodic trends work. So let's look at some elements, right? And I've got my trusty periodic table right here, just like you guys have. So let's talk about some. Let's look at beryllium, Be, and then let's look at nitrogen, and then let's look at phosphorus. All right. First, we got to be able to do the shorthand configuration. So I'll do that real quick. So if I look at my periodic table at beryllium, I go up one, go all the way over to the noble gas. So I'm going to write that configuration down. So that would be helium. So I'm going to write my He there. All right, and then that's going to be a 2s2. Saves me from having to write a lot. Now, if I go up to nitrogen, I go up one also, and guess what? I'm going to get the helium configuration, and then I'm going to write the rest of it. And it's going to be 2s2, and it's going to be 2p3. Means I've got 5 valence electrons. Now, phosphorus is one down from nitrogen, so I go up from phosphorus, and then I get neon. So that's a little different. So I get the neon noble gas configuration. Now I'm going to go down and get my rest of my phosphorus. So it'll be 3s2, 3p3. So that's shorthand configuration. We should be able to do that. So let's talk about trends. And this is really sort of important. It's going to come back, and I want you to understand it without really understanding um, the exceptions to the rules. Let's talk about the rules. We get the rules, then we can worry about exceptions later in our careers. So, first of all, let's draw these atoms and think about it, right? So, beryllium's got a atomic number of 4. That means there's 4 protons in the nucleus. 4 protons. Of course, they're positive. Okay. Nitrogen has 7 protons. It's got an atomic number of 7. I'll put that positive over the P just to let us know. I'm sorry. Oh, yeah, that is nitrogen. And then, of course, phosphorus has 16 protons. Slightly bigger nucleus. Now, let's draw the electronic configuration. So, in the first level, energy level, beryllium is going to, I cannot draw a circle with this thing, is going to have 2 electrons. The blue would be the electrons. Of course, they're negative. And then in the second energy level, it's going to have, let me go do that again. Let me do that with purple. Purple. Yeah, I got it. All right, so it's going to have, on the second level, these are the valence electrons, it's going to have 2 electrons. Okay, nitrogen on the first level is going to have the same first level as beryllium. It's going to have those 2 there, but then it's going to have 5 on the second level because you got the 2s2 and 2p3. Let's draw that second level there here real quick. Sorry, I'm not doing circles. 2 and that S, and then 3 more. Okay, now I'm going to go ahead and draw the phosphorus configuration here. So it's going to, of course, it's going to have 3 levels because it's got a 3s2. Okay, let's draw their electrons. So there's 2 in the first level. There's 8 in the second level. And just like nitrogen, there's going to be 5 in the outer level, not the same level. All right, let's draw those things in there. Okay. So, what's going on here? Okay. I've got the same shielding electrons right here as I do right there. I've only got 2. So I've got 2 shielding electrons for beryllium. I've got 2 shielding electrons. They're not valence, they're shielding. They're absorbing some of that positive proton effect. So I've got 2 right there. Okay, and then how many positive protons do I have? I've got 7 right there. And then I'm going to subtract those from there. So, I've got 4. So, my effect on these 2 valence electrons on beryllium is a 2. Okay, so there's only a positive 2 influence. So it's going to not be that much compared to nitrogen. Nitrogen's got 5 positive protons pulling in on those 5 valence electrons. Okay? So they're going to be more attracted to that nucleus. Let's look at phosphorus. Okay? So how many, I've got 16 positive. Go ahead and write that in there. 16. So how many inner electrons, not valence, do I have? Let's see. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 electrons that are going to shield that effect. I'm sorry, that's right, but did I do that right? I've got too many. Oh, I've only got 5. I'm sorry. So I've got 5 valence electrons, right? And I'm sorry, that's not 16, that's 15. My fault. Yep, 5. I've got 15 positive protons, right? So I've got a positive effect on those 5 valence electrons of 5. Okay, the same as nitrogen. Okay, the same as nitrogen. Okay, but again, they're being attracted a little bit, right? But those 10 shielding electrons that are in the inner part of that atom are blocking some of that effect from the outer valence electrons. Nitrogen only has 2 inner electrons, so they're getting more of that full effect. Plus, they're a little closer, right? So we use that formula. It's called Coulomb's law. And just to break it down, so in our numerator, we have our charges, the positive and the negative. We'll call it Q1 and Q2. I can call it Q plus, Q minus. I can call it whatever I want to. But we're looking at a positive and negative charge and their attractions to each other, right? And what's blocking them. So, beryllium and nitrogen are on the same level. Okay. There's less attraction for beryllium. There's only a 2 positive attractions sucking those electrons down, the valence electrons. So it's going to be bigger because it doesn't have the same amount of positive influence compared to like nitrogen, again on the same level. There's more positive influence is making that radius, or making that the diameter really of that atom smaller compared to beryllium. Now, phosphorus is in the same column as nitrogen, right below it, right? So there's more of a shielding effect, but there's another energy layer, that third energy layer. The second energy layer is between, and the first is making it bigger. So phosphorus would be a little bit bigger. There'd be less hold on those valence electrons because of the distance. And in Coulomb's law, the distance between the charges is in the denominator. So that's a big influence on it, all right, which makes phosphorus a little bit bigger. Now, we talked about electronegativity. Electronegativity is the ability for the atom to steal an electron. Okay? So if there's more positive charge, more positive influence, you've got a greater ability to grab an electron from another atom, right? That doesn't have as much positive pull. So if you look at beryllium, there's not a lot of positive influence. So its electronegativity compared to nitrogen would be much less, which makes sense because as you go across the row on the periodic table, electronegativity actually increases because there's more positive pull to grab that negative electron. Okay. Now, as you go down the column, electronegativity decreases, right? Because you're adding that other layer, which again is decreasing that positive influence of the nucleus, right? The protons in the nucleus. So electronegativity will decrease because you've added another energy level and there's more layers to grab that electron. Now, we also talked about, so I'm going to write that down here. So we talked about atomic radius, Then we talked about electronegativity, the ability for an atom to grab an electron or to steal an electron. Little thieves. The other one is ionization energy. And that's the energy required for an atom to lose an electron, to become an ion, a cation, right? So, there's not a lot of energy, right? There's only a 2 compared to that 5. So if you look at nitrogen, there's more positive energy, attraction, if you would, holding those valence electrons into that atom. It's really hard to pull an electron away. It would take more energy. Whereas beryllium, it would take less energy for the energy to be for one of these electrons to be pulled away by one with more stronger pull, like nitrogen, right? Now, if you look at phosphorus, all right, again, there's less energy compared to nitrogen. It would take less energy to pull one of these electrons than nitrogen, okay, and become an ion. Does that mean it really wants to? It really doesn't, right? But it would take less energy compared to nitrogen to lose an electron. So this would be less ionization energy than nitrogen. It would probably be more ionization energy than beryllium, all right, because it doesn't want to, comparatively speaking, all right. So as you go down a column, ionization energy decreases because you're adding energy layers. As you go across a table, ionization energy increases because you have more positive influence from the nucleus, less shielding for the inner electrons for them to be held together. And that's really what we need to know about trends. Okay? Atomic radius increases going down a column, decreases going across left to right the table, the periodic table, in the same period. Electronegativity increases going across the table, decreases going down a group. And ionization energy increases going left to right across the table and decreases going down. If we get that, we've got the basics, we've got the laws. Anyway, this is Coach Scott saying good luck and happy studying.